together. My name is Ben. I'm in charge of Essentium Asia Pacific. What I'm here to talk to you about today is how do we take the next step in additive manufacturing. Now, additive manufacturing or 3D printing has been around since before the World Wide Web. So it's been around for a very long time, but until now, it's really been about prototyping and created that one part that solved that one very expensive problem. So we never really had the idea of scaling this and creating an economy of scale with additive manufacturing. So what we're trying to solve and what I'm trying to convey to you today is what are the next steps that you can take in order to start thinking about 3D printing or additive manufacturing in a way that is scalable and economically sustainable for your organization in the long term. So essentially, manufacturing started millions of years ago when someone took two rocks and smashed them together, realized it made a sharp edge, and you could use that sharp edge to kill someone. We've made a lot of weapons using manufacturing. But the idea is that that person perfected the art of making a weapon, and, well, he created a product. That product became a desired item amongst his tribe, amongst the communities. That created a market, that created business. Now, over the years and the millions of years that followed, we were able to create processes that made us able to create better product more reliably, more consistently, more of higher quality. As technology evolved, we were able to implement conveyors, automation, and other sensors in there to be able to control these processes and make sure that we are living up to the promise that we are making to customers. In the last few years, we invented AI and other smart things to be able to augment these processes to create even more intelligent manufacturing capabilities. And in my opinion, Industry 4.0 is about connecting all of these layers of manufacturing together and creating value at every layer with the information created from every other layer. Now, it all starts with materials and technologies. And today I want to talk exactly about material and technologies, specifically additive manufacturing technologies and additive materials, and how to choose, how to substitute, and how to achieve a sustainable way of manufacturing parts using 3D printing as a substitute for traditional or historical manufacturing techniques. Now, a wise person once told me, and I'm not sure if he's in the room right now, no. The total addressable market of 3D printing is a function of qualified materials, the technology to print them, and the applications they enable. So without the materials, without the technologies, there's no applications. Now, there are thousands of plastics or polymers to satisfy the needs of tens of thousands of applications, but only a few hundreds of them are available for 3D printing. So we've been in the 3D printing world thinking about how we can substitute historical materials with whatever is available in 3D printable format. And we've been challenging ourselves with material substitution questions with how do we prioritize functionality over chemical resistance, how do we prioritize this over that. And really what I'm here to give to you today, and hopefully that you'll be able to take home and to your companies, is a methodology that you can assess your needs, choose a material that can substitute your historical material, and implement it in a way that is sustainable for your organization. Now, the material substitution is not new. So I'm giving an example here of what life was before plastics. Now, that was life before 1868. Now, it's a riddle. So what do you get when you take an elephant, you add a shotgun, a saw, and a lathe? Right? You actually get a lot of things because elephants, on top of being delicious, they make a wonderful source of raw material. But for their example, they make billiard balls. Now, until 1860s, billiard balls were made out of elephant tusks. And it was getting very expensive to make billiard balls. The demand for billiard was increasing, and table makers and pool halls were no longer able to supply billiard to their customers. So a table maker in the US launched an innovation challenge in 1860s. Now, if you think that you're innovative by doing innovation challenge, they existed in 1800s. So they said $10,000 to anybody who can invent a non-ivory billiard ball, right? That prize was won by a person called John Wesley Hyatt. Now, John Wesley Hyatt did not go around and invent a new polymer. He did not invent a new plastic. He took something that was invented 6 years before it in 1862, called Parksine. Parksine is the first man-made plastic derived from organic material. It was the first time that a human took a polymer, heated it up, shaped it, and cooled it down, and it retained its shape. Now, John said, wow, this is fantastic technology, but it's not strong enough, it's not stiff enough to be able to make billiard balls. So he started in the process of taking this material, adding nitrates and adding plasticizers to be able to create a material that was both strong enough and stiff enough to form a billiard ball. That was celluloid. Celluloid is a very famous material that, of course, makes billiard balls and makes film. He made money with film, not with billiard balls. Now, this person created the first custom polymer. So he said, I have an application. There are polymers out there, but they are not suitable polymers for my application. How can I reformulate it or recompound it in a way that it can meet the needs of my application? Now, this is a very familiar story to all of us because this is exactly what we're doing in additive manufacturing. We are taking polymers that exist for another application, for another industries. We are reformulating them, changing them in a way that they can be processed with new technologies to create parts that will solve new applications. So, an example of this, and this is not a part, I just found it on Google Image and it was beautiful. On the left, yes, you have a traditional light bulb, LED light bulb made out of multiple metal parts. And the idea here is that, yes, metal is fantastic. It's a heat sink. It conducts heat. It's stable under high temperatures. It can be used, drilled, tapped, do everything you need. However, it requires a lot of parts, a lot of manpower to put it together. But polymers have evolved so much that we are able to create metal equivalent polymers that both conduct heat, that maintain mechanical dynamics under heat and under stress, and in the case of the light bulb is able to replace almost a dozen parts in a single simple plastic part. Here, this process, they put the LED in the mold and they mold around it. We could easily 3D print this part and create a reasonably easy to manufacture product using 3D printing. Now, how do we go about industrializing 3D printing? So I've said 3D printing has been used to make prototypes, things that look pretty, to make parts that create a lot of value for organizations, but they only need one, so the price really doesn't matter. But when you're thinking about making 100, 1,000, 10,000 parts, well, these little costs add up to something that is not sustainable and not scalable. So, in my opinion of what does manufacturing with additive manufacturing means, it's production at scale. Now, the scale is relative to each industry. Scale for Airbus is not the scale for Apple, right? Now, it's production at scale of the same part, so you're printing over and over and over and over the same part, or you're printing the same family of parts. So parts that are geometrically similar, but they vary in small details such as diameters or things like that. Now, the idea of additive manufacturing is that it provides a lot of flexibility, right? It provides the ability to put a part into production without having to do tooling setup, without having to program your CNC or manufacture molds. So we're able to unlock business model like print to stock, of course, like natural, print on demand, and print just in time. And to do that, we need a reliable technology that will use the same process, the same work instruction, the same materials, print technologies, and of course print profile and factory file to be able to print that part or that family of part repeatedly, consistently, and at a scalable cost that will enable a company to produce parts while minimizing setup, machine time, cost, waste, and maximizing throughput, repeatability, quality, and efficiency. Now, I can share these slides with you, so don't panic if I go very fast and you can't take photos fast enough. Now, did you get that? Yeah, okay. All right. Now, the biggest mistake we make in additive manufacturing. Now, I've been in additive manufacturing for almost 10 years now. Yeah, it seems long, but it's not that long. Is that we print one part, and we're super happy, right? We have that part. It's so beautiful. It's so beautiful. We tell our loved ones, right? I've printed this part. I'm so happy today. We eat out. We go to the restaurant tonight. We have champagne. So we say, that's my gold standard. And then the next day, you come back to the office. You print another part with the same print parameters. It's not the same, not identical, it's no good. You print another part, not identical, it's no good. Another part, not identical, it's no good, right? The fact of the matter is that 3D printing will never really deliver identical parts, and it's not to us to expect this technology to evolve to a point where 3D printing will deliver 100% identical parts. There will always be room for tolerances, there will always be room for change, much like plastic injection molding and CNC. So in order to start manufacturing with 3D printing, we need to start about thinking about how do we qualify quality in 3D printing. So how do we create a maximum and a minimum of the standard, which we will call identical. Everything outside of that will be not identical and therefore rejected. Now, in practice, and this is a regular image of a gear, we have many ways to qualify a part. Example here, I'm qualifying a measurement. This measurement cannot be less than 0.563 and not more than 0.564. So if I were to manufacture 1,000 units of this part, I would get a distribution. I would have a certain distribution of parts where certain parts fall below or above that threshold, creating identical and non-identical parts. Now, we're able to do a distribution with this of anything that can be measured or quantified. That's continuous use temperature, dimensional accuracy, hardness, flexibility, strength, impact, conductivity, and so on. Essentially, we are able to create a quality standard out of multiple criterions, and we are able to qualify each part based on this collection. Now, so what makes a good printer? Now, we have thousands of printers available on the market that produce different technologies, that produce parts in different processes using different materials. Now, a good printer, in my opinion, is a printer, regardless of price, origin, or technology, that is able to create the part that meets your quality standard within a single standard deviation. So when you have a part and you're producing 1,000 of them and you have that distribution of parts, you are able to constantly, within a single standard deviation, achieve your quality standard. On the other hand, a bad printer, there's no such thing as a bad printer, but a less good printer, is a printer that would not be able to meet the single standard deviation within your quality standard. So the printer offers too much variability in its manufacturing process and offers too much variability in its features that it delivers and cannot deliver a part that meets your quality standard. Now, a manufacturing printer, an industrial printer, is a printer that is so accurate that it not only delivers all its parts within the single standard deviation, but might be able to deliver it within 1.5 or 2 standard deviations of it. That means that even if you are making mistakes while producing your parts, they are still good enough to meet your quality standards. And this is where we want to focus on. I'll skip that. Now, with materials, we have, like I said, hundreds of materials. There are thousands and thousands of materials. And for materials for our specific applications, there's a list of materials. There's a line somewhere. Everything above that line is good. Everything below that line is bad. Boom. Right? So we have technologies that we need to select. We have materials that we need to select. And we need to select these two based on the design of our part and on the economics of manufacturing this part. Now, what is available to 3D print today? Now, I did not do an exhaustive list in this little pyramid here, but the idea is that we have ultra-performance plastics that can be 3D printed on multiple different technologies. PEEK, PEC are very good in high-temperature applications, and they're very chemically resistant, and they're very stable. Now, on the right-hand side of this slide, I'm putting the ambient processing temperature, so the temperature at which the processing chamber needs to be in order to manufacture these parts. A high-performance material like PPSU, like PEI, like PEHT, is also very good, being processed at a temperature of 150 Celsius. Engineering-grade materials, polycarbonate, PMMA, POM, PCTG at 100 Celsius, and then commodity plastics, PLA, PP, HDPE at below 100 Celsius. Now, when you're thinking about, well, I need a printer that is able to print the materials that I need, and if you're buying a printer ahead of time, well, you say, well, I need a printer that is able to have the widest material compatibility possible in order to achieve manufacturing capabilities. Now, if you're buying a printer that is extremely restrictive, you're limiting to what this printer can deliver to you. It is not a universal tool. It is a tool that is limited in itself. So you might want to choose a printer that is able to overcompensate or achieve higher levels than you require for your manufacturing processes. A professional printer can accommodate mostly commodity plastics and some engineering-grade plastic, and what I call desktop is commodity plastic printers. Now, we talk about amorphous and semi-crystalline a lot in the world of polymers, and not a lot of people, including myself until last week, knew exactly what they were. I'm a machine person, I'm not a materials person. Now, I like to think of noodles. Now, noodles move around in your bowl of soup like noodles in a bowl of soup, right? And as you're adding heat to this polymer, which is essentially a cake of noodle, these noodles can move freely against one another, right? So that's what we call amorphous. Now, semi-crystalline noodles is when you let your noodles tip over the side of the bowl overnight and then the next morning they're all dry. These create little crystals, so there's perfectly aligned little bits of noodles that are stuck together all over the plastic, surrounded by noodles that are soft. So when you're moving these noodles in your bowl, they're actually hard to move because they've got crystals of little hard noodles around them, preventing the motion. That's the simplest way of explaining it. But essentially, you have noodles that are polymer chains that are partially organized into crystals or in tightly packed bundles that are moving freely against other tightly packed bundles of polymers. Now, when we're considering the two, there are, of course, advantages and disadvantages of each amorphous and semi-crystalline material. Now, amorphous materials, I feel they behave a bit more like liquids, where you increase the temperature, their viscosity will decrease, so they will become more and more liquid. They will reach a temperature, a glass transitioning temperature, at which point it will lose all mechanical properties and become essentially useless. Semi-crystalline materials, because of these little crystals, create friction amongst one another. Yes, there is that first glass transition temperature where the chains connecting these semi-crystals are, liquid, but because there are still crystals in there and they're still tightly bound together, they are creating friction and they create a second plateau, a second functional area in the polymer at that temperature range. And this is where we want to focus our attention. We want to be able to operate a polymer at high temperature without too much compromising on its mechanical properties, dimensional accuracy, and without decreasing or increasing its brittleness. But as we see, semi-crystalline materials lose a lot of their strength at the glass transition temperature, so much so below the amorphous materials. So how can we increase this second plateau? And the secret is really fiber reinforcement. Now, the word fiber, people consider it as carbon fiber, glass fiber. There's actually a lot of fillers that we can add to polymers in order to be able to increase their mechanical strength and their resilience to heat. Now, what is fiber and how does fiber work? Now, when we see a semi-crystalline material under a microscope, we see kind of these, well, they're not in color, they're more black and white, but you see these beautiful little objects there floating around in a pool of liquid. Now, when we add fibers to it, what happens is that it creates nucleating sites that not only adds barriers for movement in this pool, but also bind these little crystals to one another. So as you can see here, and here in this drawing. So the idea is that it's not only creating, like I said, obstacles that prevent movement, but it's binding them. Therefore, it's not crystal rubbing against each other and preventing motion. It's a rod of fiber that is connecting multiple crystals, creating a long rod of crystals together, increasing the strength and further adding difficulty in basically resistance to heat. Now, the influence of length of fiber also affect your performance. So there's really long fibers, we call it short fibers and long fibers, and the cutoff is arguably around 1 millimeter. Anything below 1 millimeter is called short fiber. Anything above 1 millimeter can be called long fiber. Now, we want to be able to, when we choose a material and we say we need it stiffer, we need tougher, we need it stronger, we can say, oh, we'll put 100 millimeter carbon fiber segments in our filament, right? In our powders. Yes, that's true. You can get, but that increases the cost of your materials and make it unsustainable. Now, when you add even a little bit of powder, of fiber powder to any semi-crystalline material, you immediately have an impact on stiffness. You add longer fibers, you add strength. You add even longer, you add toughness. Now, if your application requires extreme toughness or strength or stiffness, yes, you can look at very long fibers in your polymers. But if you're only looking to have perhaps the continuous heat temperatures of use temperatures of a polymer and have just simply a bit more stiffness to it, you can really just add a little bit of carbon fiber to it, or glass fiber, to increase its stiffness without necessarily increasing the cost dramatically of your polymer. Now, this is where I would like you to pay the most attention. Well, of course, at my name as well, so you don't forget who I am, is that how do you choose a 3D printing material, 3D printable material? Now, we talked about, oh, sorry, I won't show that right away. We talked about there are only a few hundred materials that are printable. We need to select them, right? But each material, when they're processed, change. They are no longer maintained their intrinsic mechanical properties when they are processed with heat or with any form of manufacturing technologies, as well as the design of the part is relevant or is affected by the process that manufactures this part and by the material that is manufactured. So the first step is really, when you choose a polymer, you understand your application, and you try to choose the polymer that has the closest intrinsic material property as what the application requires. Now, that is basically the suitability to meet the environment requirements: chemical resistant, flame retardant, surface energy, temperature of continuous heat, continuous use, or heat deflection temperature, as well as some mechanical properties that are intrinsic to the polymer, such as strength. Once you have identified that polymer, you have to look at what is the process or what the technology that can 3D print that polymer, right? How does this technology, well, one, affect or impact this polymer and changes its behaviors? How is it available in your area? Is it available to acquire? What are the facility requirements to have this technology inside your facility? And what are the post-processing requirements and supply chain required for this material and this process? Now, this is very important, because this is where we're starting to think, okay, well, I've got a polymer, I've got a machine, but the machine is $1 million. Is it really make sense to start making 100,000 parts out of this machine? Maybe, maybe not. The next step is looking at your design. Now, your design will have huge impact on part consistency and on repeatability. If you have a design that's designed for additive manufacturing for this specific technology, taking into consideration this material, you will be able to have a repeatable and consistent part coming out. If your part is badly designed, even though your material and process are excellent, you will have a bad part. Now, we're looking here for things designed to increase cosmetic appearance, designed to increase dimensional accuracy, designed to increase part consistency, and mechanical properties that are affected by the print process. Now, when we are thinking about intrinsic mechanical properties like strength, yes, that belongs to the plastic. But when we are thinking about print orientation that does affect mechanical properties, that relates to the process of manufacturing this part and the design of this part. So if we are able to do intelligent design of our part, we are able to overcome the limitation of the process and the consequences of this process. Now, finally, we have business matters, and that's the most important things really, is that if you can make money, earn money, or save money using this technology to implement this new way of manufacturing parts in your factory, and really, will it help or will it be too expensive? Now, this is a 4-letter word that I've invented today. It's called MPDB, and just so you know, it's material, process, design, and business. Now, why is this 4 steps very important? Now, to illustrate this, I've taken our materials in order of heat deflection temperature to illustrate. Now, imagine that you're looking at substituting a plastic or a metal, and you say, my application requires continuous use temperature of 150 Celsius, right? Well, there are a lot of materials that can be printed that can support 150 Celsius continuous use temperature. Now, when you're thinking about 150 Celsius, you're saying, oh, the immediate answer, oh, you need PEEK or Ultem. Yes, PEEK or Ultem are very good materials, and they're very good at handling 150 Celsius in continuous use, but they're also very hard to process. They require a high temperature extruder, they require a heated chamber. Generally, they require a machine that is more expensive than a machine that can process plastics at below 300 Celsius. But by investigating further, you're able to find, well, hey, there is a polymer that has a continuous use temperature of 150 Celsius that is processable below 300 Celsius and that is cost effective. So the idea is that if we are not looking at all the available materials in the 3D printing ecosystem, we might be choosing the wrong material. Now, how do we choose a substitute material? Well, of course, we look at the historical part. We all know our historical parts. We know how they're used. We know what they're used for. We know what they need to be good and what they don't need to be bad. So we start with the material. We choose a material. We choose the process that can print this material. We choose a design that optimizes or maximizes the value of this process and this material for this part. And then we look at the scalability, sustainability, and business matters for this combination. We will do this iteratively. It's going to happen quite a lot until we find the right material, right process, and the right design for the right price. And yes, we might find a part. Very likely we will. There's a lot of materials out there, but maybe we won't. Sadly, not all materials are available, and sadly, they don't correspond to all the applications out there. So what if the material doesn't exist? Now, the first step in creating your own material, now creating your own material is not expensive. Well, it's more expensive than buying a spool of material, but it's not astronomically expensive or prohibitively expensive when you're thinking about manufacturing 100 or 1,000 or 10,000 units of a single part. Now, you start with a polymer as close to the historical part's mechanical properties or environmental capabilities, which can be amorphous or semi-crystalline. Now, an amorphous plastic, you will be choosing that for visual properties, transparencies, high dimensional accuracy, ease of processing, and cost effectiveness. Amorphous plastics are extremely cost effective. They're extremely easy to process. They're dimensionally accurate, and essentially you can print them without having too much difficulty. A semi-crystalline polymer, on the other hand, has a lot of stress. It warps a lot. It is intrinsically not dimensionally accurate. And yes, it does offer nice mechanical properties and nice chemical resistance properties, but it's extremely difficult to process. To make it easier to process and to improve its dimensional accuracy, we can add fillers, thermally conductive fillers and non-thermally conductive fillers. The idea is that for the example of the light bulb, we want a thermal conductive filler so that we can dissipate the heat. Non-conductive fillers we might want to use for things like friction where there's no heat involved. Non-conductive or non-thermally conductive fillers are usually significantly less expensive than thermally conductive fillers. Once we have decided on our polymer and on our optional filler, we can start looking at how we need to adjust the molecular length of our polymer. Now, the longer the polymer chain is in our material, the stronger and truer the mechanical properties will be. However, it will be increasingly difficult to process with a 3D printer. Now, once you have an idea of what this balance is, we have to look at what are the additives that we want to add to tweak this material in order to achieve the final functionalities of our polymer. If we're looking for flame retardants, if we're looking for conductivity, if we're looking for other things that are added to a base polymer in order to deliver on an application, it is the very last step. Now, we need to balance all of these criteria together in order to create a polymer that is not only functional and suited for your application, but that is processable and cost-effective. So, how do we refine a polymer? We start again with our historical parts requirements. We start by prototyping a first polymer, looking at the process, investigating how can we process this polymer, how can we design a part that maximizes this processed polymer, and what is the business around that. And yes, we'll iterate around that, doing multiple formulations until we can get a part. Most likely here, there will always be a solution because there is an endless amount of polymers we can work with. Now, finding the right material for your application is the difference between too expensive to try and sustainable at scale. And this is really what we need to look at, is we need to find the right polymers that satisfies the exact requirements of an application, the technologies that can process them at a cost-effective way in order to be able to deliver at scale a part. Now, what am I doing to help? Oh, I'm over time, I'm sorry, I've got 2 slides or more. What am I doing to help? Well, I'm in Asia. I'm building a network of innovation centers. So I'm building, in the next 3 years, my target is to build 11 centers, application and material qualification centers, where we'll be working hand in hand with our customers to develop, certify, and qualify materials. This year, we're launching in Singapore, in Tianjin, and in Shanghai. Next year, Shenzhen, Taipei, Penang. In 2021 in Japan and in Korea, in 2022 in Vietnam, Thailand, and Indonesia. The idea is that we need to have industry-specific teams that are able to unlock and to educate and develop the competencies and capabilities of industries and companies in order for them to make the transition to additive manufacturing. So our process, 3D, so discover, demonstrate, and deploy, where our focus with our team across regions specialized in different industries is really to understand the production needs, the requirements, and the scalability metrics of what makes additive manufacturing a success in your organization. To demonstrate this through a proof of concept and proof of value project, and to help you roll it out throughout your organization. Now, we have a few key exciting things, and these are my last slides. Now, when we think about 3D printing, we think about sausages. I'm not German, but I do like sausages. Now, the idea is that with 3D printing material, we're always used to having homogeneous solutions, right? Homogeneous resins, homogeneous powders, homogeneous this and that. Well, with filament, we're able to create a multi-dimensional feedstock, where we have an inner core of material and an outer core of another material. Now, this means we're able to add high-value additive coatings on the outside of the filament that will be translated to the outside of the part. So if we are adding, for example, yeah, 1 second. Good? Okay. Sorry, I like people to take photos. Now, one of the 3 examples we use this technology for is creating Esd-Safe Material. Now, we've created the only clean room safe 3D printable material by creating a thin layer of carbon nanotubes along the entire length of the filament. As this is being processed through the extruder, this is being translated directly to the exterior of the part. So we're able to put anything inside. So we have PCTG, high temperature nylon, TPUs, PEEK, and so on, in order to be able to deliver ESD materials at different room temperatures and in different mechanical loads. We are using it to create highly volumic ratio of fiber-filled materials. Now, when you're thinking about 25% medium-length fibers, and I'm talking medium-length fibers in your filament, and you're extruding them through a small hole, these things will compress and then expand. And as they're expanding, they're separating your layers of your part, and they're sticking out of your part, making an extremely abrasive part. Now, we want to increase the adhesion between layers, so by creating a little sausage with a tough polymer casing around it, we are improving containing these fibers inside, so retaining the strength of the material while increasing the layer-to-layer adhesion. And the last example is processing extremely soft TPUs. Now, TPUs normally are very hard to process in filament form below 90A. We are able to process an 80A TPU in any printer. Simply that we've developed an outer coating of harder TPU that provides just enough rigidity to be able to process it within any FDM printer. Now, our second innovation is a flash fuse. We call it flash fuse. It's a plasma gun inside the printer. What we do is that as it's printing, we have a plasma ray that is doing plasma welding. I like the word plasma. I'm sorry, I'm repeating it a lot. We are plasma welding each layer to the previous layer together. So what we are able to do is that we're able to achieve the XY strength in Z as well. So not only are we able to create an almost isotropic part with FDM, we are able to create a near plastic injection molded part in terms of mechanical properties and in terms of stiffness, toughness, stretch, strength, and stretch or flexibility. Now, these are the ways that we have evolved the 3D printing technology in order to create stronger parts. Our printers are printing at 200, 300 grams an hour. We're printing what another company can print in 5 or 6 hours in 40 minutes. And it really is unlocking these new business models. So I'd like to thank you with this last image. My name is Ben. I use WeChat because I'm in China most of the time. So please add me. If you have any questions, my booth is outside. I'm here until 6 p.m. and I'll be on the panel at 4 p.m. Thank you very much. Sorry, I clapped myself.